This is a dodecahedron that I recently made from strips of cardstock. Each edge gets a fold down its length in order to give it some structure, and then the ends are folded at an angle to form a dog ear to give a gluing surface to each of its neighbors. I 3D printed this jig to fold the dog ears at the same angle every time, and it just snaps on to the sides of the paper to keep it aligned. Later in this video, I'll show a demo that demonstrates the relationship between the valley fold angle and the angle that the dog ear makes. But first we'll look at some of the earlier prototypes that I made. Here is an icosahedron just from regular copy paper and stapled together. And besides the copy paper not holding its shape very well, you can see that the relationship between the fold angle and the dog ear angle, the angle that it makes with respect to the center line, is not quite right, and it gives it kind of a ruffled appearance, which is kind of cool looking, but is not what I was going for. And here are some other shapes. A tetrahedron, which also you can just tell by looking at it doesn't have the right angles, and a pentagonal bipyramid, which is a demonstration that you can mix and match different angles and still end up with a nice shape. Before this piece buckled right here, this structure was fairly strong for its construction of just paper. So here is a Blender file that has our piece geometry laid out with a master piece at the origin here, and it is then instanced to each edge of a dodecahedron. I added some custom properties with the scripting API and added some sliders to control them. So you can see here the major fold angle. As I change that, it changes the rotation about the y-axis and updates each instance accordingly. There you can also control the dog ear angle, which is the angle from the y-axis that the piece makes, and finally the fold angle, which determines the angle relative to the crease line that it's folded. After setting up these three separate controls, I was finally able to work out the correct formula that, given a fold angle, will derive the proper dog ear angle. So with this last slider, as I update it, it will update both the fold angle and the dog ear angle, and keeps the intersection point consistent. The dog fold angle is not implemented, and it's still something that I'm working on. So starting with the dodecahedron, we can extrude each face along its normal and then bevel the edges. And you can see that our piece geometry is equivalent to this shape. The rectangle simply extends to include this missing area right here. Here is a section view looking along one of the edges. You can see that this blue angle down here is actually the dihedral angle, which is the angle between the faces on a dodecahedron, and the angle up here is what we've defined as the valley fold angle, which is the angle from the y-axis in this case. And we end up with a triangle that we're interested in getting this angle here. So after working that out, we can jump to this view, which shows that the angle we're interested in working out is this blue one, which is the dog ear angle, as I've called it, which is the angle from the x-axis from this view, the red axis, which is how much we need to fold the paper on the ends. We can see that the blue angle here is the one we're interested in working out. This orange angle is the same one we were looking at in the other view, and this green one is simply half of the interior angle of a pentagon. So we know this green angle and we know this orange one, and we're interested in working out the blue one. To do that, we can arbitrarily call this edge here 1, and then using tangent we can get this edge with the green angle, and we can get this edge with tangent since we now know this edge and the orange angle, and finally the blue angle is written in terms of those. So that's a nice way of determining the angle relation for a regular shape where each edge is identical to the next one. If you have a more complicated shape that is not regular, or at least not regular in each edge, then you need another method in order to determine what pieces you need. So here I'm starting with a truncated dodecahedron, and I can generate the proper set of edges with a script that walks through each edge and intersects it with its neighboring edge on each face that it's a member of, and shows you each piece that you need. And if you wanted to build a model of this, then you'd want to know which pieces are actually the same, and so it actually goes through and counts which are of the same edge length and of the same angles at each of its corners. And you can see here we actually get a cut list showing the angle in each corner and the length of that piece in arbitrary units. So one neat thing to do once we have all of these edge pieces defined is to imagine transforming one edge to the other by way of specifying the location and rotation, as you can see with this coordinate axis, which is placed on the midpoint of the edge piece. We can transform one edge into the other by interpolating between those coordinate frames. And if we choose an ordering so that one edge goes to another and then that edge might go to another, etc., until we've gone through all 30 edges, then we could shuffle the edges. And a nice way of generating a shuffle like that is using Sotolo's algorithm, which is a variant of Fisher-Yates shuffle, which guarantees that the cycle length of the permutation we come up with is equal to the number of edges that we have. In other words, each edge visits every other edge exactly once, and no two edges occupy the same edge location at any given time. So you can see as I step through this animation, we interpolate between coordinate frames, and now we're at a new shuffled edge set. And we just need to repeat this another 30 times, and our original edge ends up back where it started. And so here is a rendered animation showing that now.